Welcome to The Explainer. Today we are stepping right into the middle of the controlled chaos of a high-end kitchen. Why? Well, it's the perfect way to understand one of the most crucial jobs your computer does, deciding what to do next. We're going to see how your computer's brain, the CPU, juggles millions of things at once without ever dropping a single one. So picture this. You are the head chef in a restaurant that is absolutely packed. Orders are just flying in. Some are simple salads, some are these super complex entrees. Here's the catch. You've only got one pair of hands. How in the world do you decide what to cook next to keep every single customer happy? This is the exact problem your computer's CPU solves every single second of the day. The chef, that's the CPU. And all those customer orders? Those are the programs and apps you're running. Okay, so before our chef can even think about cooking, they've got to understand the orders, right? In computer speak, that means we need to get a handle on what we're actually scheduling. And this brings us to two really key ideas: processes and threads. Let's break this down. A process is like the entire recipe on the order ticket. Make one lasagna. It's the whole job from A to Z. A thread, though, that's just one tiny step from that recipe. Think boil the pasta or grate the cheese. A single process, that one lasagna, can have dozens of these smaller threads. So you might be asking, why even bother with all these little steps? Well, because it is unbelievably efficient. It's kind of like having a whole team of cooks in the kitchen. One can be chopping veggies while another one is boiling pasta. That's parallelism, doing different things at the exact same time. And if the oven's busy, a cook doesn't just stand around waiting. Nope, they can start prepping a salad, which makes the whole kitchen feel way more responsive. And the best part? They all share the same kitchen and ingredients, which is way cheaper than building a brand new kitchen for every single dish. All right, we get it. We've got our orders, we've got our recipes. Now for the main event. How does our head chef actually choose what to do next? This is the real heart of CPU scheduling. They use a rulebook, or what we call algorithms, to manage the absolute chaos of the dinner rush. To see how these rules really work in practice, let's look at tonight's orders. So at time 0, boom, an order for soup comes in. It takes 8 minutes. A minute later, a 4-minute steak order arrives. And a minute after that, a super quick 2-minute salad. We're going to use these 3 orders to put our chef's different strategies to the test. Okay, strategy number 1 is the simplest one, and you could argue it's the fairest. It's called first come, first served. It is exactly what it sounds like. Just like waiting in line at the grocery store, the first order that comes in is the first one the chef works on. No cutting, no exceptions. Let's walk through this. The soup order came in first, so from minute 0 all the way to minute 8, our chef is completely tied up with soup. Only after that soup is totally done can they even start the steak, which takes another 4 minutes. So finally, at the 12-minute mark, our poor chef can finally get to that simple 2-minute salad. You can see how that one long soup order just created a massive traffic jam in the kitchen. So here's the bottom line. First come, first served is beautifully simple. It's totally fair. But man, it can be super inefficient. That poor little salad had to wait 10 whole minutes just because it arrived last. This is actually a known issue called the convoy effect, where one big, slow task holds up a whole bunch of small, fast ones right behind it. Okay, but what if our chef decided to prioritize speed over fairness? Well, that brings us to our second strategy: shortest job first. With this rule, whenever the chef is free, they scan all the waiting orders and they pick the one that's going to take the least amount of time to finish. It's all about efficiency. Let's see how this changes the game. So the soup still has to start first because at time 0, it's the only thing to do. But look what happens at minute 8 when the soup is done. Now both the steak and the salad are waiting. The chef looks at their cooking times, sees the salad is just 2 minutes versus the steak's 4 minutes, and makes a smart move, knocks out the salad first, then moves on to the steak. This is a perfect example of why shortest job first is so powerful. It's often the best way to minimize the average wait time and just get the most dishes out of the kitchen fast. But there is a dark side. A really long, complicated dish might get ignored over and over again if a constant stream of quick little jobs keeps coming in. This is called starvation, and it's a very real risk. So we've seen fair and we've seen fast. What about responsive? This is where round robin comes in. In this system, the chef is an absolute master of multitasking. They'll spend a small, fixed chunk of time, let's call it a time slice of 3 minutes, on one dish, then immediately switch to the next dish for 3 minutes, then the next, cycling through all the orders until they're all done. Let's watch the chef juggle. From minute 0 to 3, they work on the soup. Then they switch to the steak for 3 minutes. Next up, the salad. Now the salad only needs 2 minutes, so it gets finished right there. Great! The chef then cycles back to the soup for another 3-minute burst. Then back to the steak, which now only needs 1 more minute. And finally, they go back and complete the last 2 minutes of the soup. The key here is that every single customer sees that their dish is being worked on almost right away. The huge advantage of round robin is that it feels incredibly responsive. Nobody is left waiting forever before their order starts getting some attention. The downside? All that switching takes time and effort. The chef has to clean their station, grab new ingredients, and refocus their brain. In computer science, we call this context switching, and it's basically the overhead, the price we pay for that amazing responsiveness. Okay, so we've looked at 3 really different ways of running our kitchen, but how do we decide which one is actually better? We need some cold, hard numbers. Let's talk about how we actually measure our chef's efficiency. The first metric is called turnaround time. Now, for the customer, this is the big one. It's the total time from the second they place their order to the second that food is on their table ready to eat. You can think of it like a trip to the grocery store. It's the time from when you walk in the front door until you walk out with your groceries. It's the total time you spent getting the job done. But there's another really important metric: response time. This measures how long a customer has to wait before they see any sign of progress. Let's go back to our grocery store analogy. This is not the total time you spend in the store. It's just the time you spend waiting in the checkout line before the cashier actually scans your very first item. As we saw, round-robin scheduling is absolutely fantastic for keeping this number super low. Now, our single chef has been working their tail off. But what happens when the restaurant gets so popular that one chef just can't keep up? Well, you hire more chefs. And in the computer world, this is called multiprocessing, using more than one CPU to get the work done. And there are basically 2 ways to set up this multi-chef kitchen. In what we call a symmetric setup, you've got a team of equals. Every chef is a head chef. Any one of them can grab any order from the queue and get to work. But in an asymmetric setup, it's more of a classic kitchen hierarchy. You've got one master head chef who's in charge, and they assign specific, smaller tasks out to a team of assistant chefs. So after all of that, what have we really learned? The most crucial point is this: there is no single best scheduling algorithm. It is always a trade-off. Are you building a system that needs to be incredibly fair, like first come, first served? Or one that needs to finish the most jobs in the shortest time, like shortest job first? Or do you need a system that feels super responsive to a user, like round robin? The best choice depends entirely on the goal. And that brings us to our final thought. Let's make this real. Imagine you are put in charge of designing the operating system for a hospital's critical life support machine. This is a system that can never, ever be slow to respond. So what kind of scheduling rule would you choose? Do you prioritize fairness, raw speed, or immediate, predictable responsiveness? The answer isn't easy, but it's a decision where lives are literally on the line. Think about it.